Hey everybody, welcome back to another round of physics, and yeah, let's get going. I thought that we should probably have a second video dealing with using polar coordinates, and maybe we'll go into even spherical coordinates, but trying to get a sense of how to use these different coordinate systems to do integration, say, in 2 or maybe even 3 dimensions. So to start off with, let's remind ourselves that polar coordinates, rather than using something like x, y, and, well, let's stick in 2D for a second. Instead of using coordinates like x and y, we use the ideas of r and theta, the distance from the origin and the angle that it makes with the x-axis. And of course, we know how to relate these two via drawing a triangle on the coordinate axis. So I'll put Cartesian coordinates here. And we notice that r is simply given by the Pythagorean theorem. And then theta is simply given by the inverse tangent, which you already know just from dealing with vectors in general. So there's that. Of course, you could go the other way. You say, well, given r and theta, how could I find x? And again, you know the, for lack of a better term, I would call these the inverse transformations. Knowing r and theta, you can derive x and y accordingly. Okay. So the first thought I had was perhaps we should do a situation where we are using the polar coordinates to calculate something like, I don't know, the force of a ring on a point charge. Okay. So let's go ahead and set up a situation. I guess we'll find out. Let's go with 2D. So again, so let's go ahead. Let's put a point charge of, I don't know, positive E, put plus E right here at the origin. Okay. And I don't know, let's do something fancy. I mean, if we did a full ring, we could use symmetry arguments to argue that it's 0. Why don't we do like a quarter ring here? So we'll say that we have a quarter ring of charge Q and radius R. Okay. And the question we would like to find out is, what is the force on E due to the quarter circle? Okay, question mark. Okay. Yeah, good. Okay, well, let's just briefly remember what kind of steps we need to follow here. So generally, since we already know the charge of the system and we know the charge of the surroundings, basically the little things that we need to figure out are how to express the infinitesimal amount of charge in each of those line segments. So we'll have to come up with some sort of idea about, for lack of a better term, I'll call it dq. Okay, so we'll need to find an expression for dq. Second of all, aside from finding that expression for dq, we will also need to find the position vector of that little segment of charge. And I guess you could say we would need to find the position vector of our system charge as well. In this case, we went ahead and put the system at the origin. And so the position vector for that particular piece is simply 0, 0, 0. Usually it's nice to do something like that when you're given the opportunity. And then lastly, what we'll have to do is we'll have to go ahead and figure out what the unit vector is between our infinitesimally small piece of charge in our system. And then we'll have to do our integrations, because remembering, we're not talking about total charge capital Q, we're talking about these little infinitesimal segments. Well, let's go ahead. So first off, we will go ahead and assume a uniform charge density in that semicircle or that quarter circle. Excuse me. And so we'll go ahead and say, okay, well, if it's a uniform charge density, okay, we can think of the total charge, which was given by Q, divided by the total length of the object. So we have to go through and, okay, well, 2 pi r is the circumference. We have 1/4 of that. And so we have 1/4 of 2 pi r. There is the total length of our quarter circle. Of course, on the other side, we could think of this as being the amount of charge in a tiny, tiny little arc length. Yeah, good. Okay. Well, here we will go ahead. I mean, in some sense, you could rearrange. You could say, okay, well, that's a piece of cake. That means that it's 2q over pi r times my infinitesimally small arc length is equal to my small piece of charge. What is the infinitesimal arc length when we're thinking about polar coordinates? Yeah, good. You say, well, the arc length is given by the radius of the circle times the small angle. And so I'll go ahead and plug that in. We have 2q over pi r, and then r times my infinitesimally small angle. So step 1 is done. Right? We said we need some sort of expression for the infinitesimal charge. Well, let's go ahead. We should go on to step 2. And there we need to know the position of that infinitesimally small charge. And now, I don't know, for some reason it's me. I always, perhaps it's because Cartesian is just the easiest to conceptualize. Perhaps it's because Cartesian's been drilled into my head for a far longer time, like, middle school onwards. I always have trouble thinking about stuff in terms of polar and spherical and that kind of. So usually what I end up having to do is think about, okay, well, the position of that is given by x comma y and 0. Right? So I always start thinking in Cartesian. And for me personally, I have to convert it over to polar. So I know that my x component is given by r cosine of theta. And my y component's given by r sine of theta and 0. And for sake of argument, I'll go ahead and pull the r out, that common factor of r, partially because I am 100% lazy. There we go. The relative position vector between my system and my source is equal to the position vector of my system minus the position vector of my source. Now, the position vector of my system is all zeros. And so at the end of the day, I get negative r cosine of theta sine of theta 0. Well, now, we could go ahead, but we know a trig identity. We know that cosine squared plus sine squared is equal to 1. And so because I've written it in this form, we immediately know the magnitude of that relative position vector is simply r, which should make sense, right? The position vector for the infinitesimal charges is basically the radius of the circle. And furthermore, we know that the unit vector pointing from our source charges to our system is given by negative cosine of theta, sine of theta, and 0. Right? In other words, it's opposite direction of the position vector for the source charge. So the position vector for the source charge points from the origin out to the charge. And when I put the negative sign in, it flips that vector direction. So it points from the source charge towards to the origin. Well, now we've got all of the individual pieces. We have the Coulomb constant, we have the charge of the system, we have the expression for the infinitesimal charge at each location, we have the position vector and the relative position vector and the directions. So now let's go ahead and just plug that all into Coulomb's law. Remember, our overarching goal is to find the net force. And so what we have is K. I'll write it in the most general form first. And for our specific situation, we're told, okay, we have a charge, a system charge of E, fundamental charge. Here we have our source charge as some dq. The magnitude of the relative position vector is simply the radius of the circle, and we'll square it. And lastly, we said the unit vector representing the relative position vector is simply negative cosine of theta. Oops, excuse me, I dropped that negative sign, sine of theta, and 0. So I'm moving that negative sign that I had expressed out front. I'm just going to distribute it inside. You don't have to do it that way. That's me. Well, let's go ahead and recall this is the contribution to the net force. This is the infinitesimally small contribution to the net force due to that small charge. Well, let's go ahead and substitute in the expression for that small charge. We have E over R squared. And here we note we had a 2q over pi. Those are all constants. And we had a d theta. And just double check real fast, right? I'm not lying to you. There's the 2q over pi d theta. And then, of course, we have our negative cosine of theta, or negative sine of theta, and our 0. Now that's all left to do is take the summation. So we need to do the summation. And what we'll do is we'll break it into components. So let's go ahead and first of all consider the net force. And specifically, we'll look at the x component. Well, that is, let's note that all of the stuff out in front, those are just constants, so they need not be involved in the integrand. And then I basically have the integral of cosine of theta d theta. Go ahead, ask yourself for a second. It's always good. I tend to just put in the limits of integration, right? Stop and ask yourself for a minute, what are the limits of integration for this case? Yeah, good. 0 to pi over 2, right? We said a quarter circle. Well, we started at the origin, pointing along the x-axis, which is an angle of 0. And then we went a quarter of the way around the circle until we were at the y-axis. Okay, well, let's go ahead. Of course, you being astute and proficient and persistent and hard-working members of the calculus classes know that the integral of cosine is sine. Remember, sine of theta. And we're going to evaluate from 0 to pi over 2 and 0. And so at the end, we will need to evaluate at the upper limit of integration and the lower limit. Now, before you pull your calculators out, these are, sines, cosines, usually you don't have them memorized, but certainly sine of 0, sine of pi over 2, those are ones that you should have in your memory bank. So take a minute, see if you can remember what those are. Good. Sine of pi over 2 is 1. So this is 1. And sine of 0, that's 0. So at the end of the day, we get that the x component of the net force acting on our system is negative 2k EQ over r squared pi. Good. Not so bad. Of course, we did it in the right coordinate system. If we did it in Cartesian, trig subs, yada, yada, yada. All right, well, let's go on to the component of the net force acting in the y direction. And again, we have a negative k e q. We had that 2 out in front. We had the pi and the r squared. But instead of a cosine, we had a sine of theta. Excuse me, I should put this as a little d. Right? And so, d theta. Forgot about that. And so we would like to integrate that rigmarole with the limits of integration of 0 to pi over 2. So same song and dance. What is the integral of sine of theta? Good. And that one is negative cosine of theta. So we get a 2k EQ pi r squared, excuse me. And we have a negative cosine of theta, evaluated from 0 to pi over 2. Now, just because I'm always worried about dropping my negative signs, when I see 2 negative signs, I'm just going to make those positive signs there, just so I don't screw something up later. We get a 2k EQ over cosine of pi over 2. Yeah, good. That one is 0. And then we have minus cosine of 0. What's cosine of 0? Yeah, good. 1. This is a 1. So at the end of the day, I get a negative 2k EQ over pi r squared. And that is the net force, the y component. You say, wait a minute, I've seen that before. Yeah, indeed. Let's see. Notice that the y component is exactly the same as the x component. Not by accident. You should ask yourself, though, when that comes up, you should ask yourself, does that make sense based on what I was dealing with? And hopefully it does. You notice if we go back to the original idea, and I'll redraw it here, what did we have? We had an x, a y, and we had a circle, a quarter circle. Okay. Now, generally, and this is a nice idea to kind of keep in mind as you go through physics. You never know where it's going to rear its head. But what I'll say is that generally, if you can find some sort of symmetry, that ends up being important in the problem. Okay. So for this situation, we notice that there is some symmetry, namely, because this is a quarter circle, at 45-degree angle, and I apologize, this is of course going to be ugly. At 45-degree angle, you notice that for every piece of the circle here, there will be a similar piece down here at the same angle with respect to that dashed line. In other words, here is an angle, I'll call that angle phi, and we have a same piece at a similar angle of phi. So what will happen is that the component, you can think of, let me call this piece 1 and I'll call that piece 2. The force due to piece 1 will be in this direction. The force due to piece 2 will be in that direction. And you notice that the components of each of those forces the component that is perpendicular to the red dashed line. So this component, and I'll draw a second one in right here, that component, those two components are in opposite directions and they will cancel. The two components that are parallel to the red dashed line will add. And so if I'm thinking about just those two red arrows, I should get some sort of addition along the red dashed line. So at the end of the day, I expect the net force to be in that direction, the red dashed line located at 45 degrees. Now, of course, that's all contingent on the linear charge density in that curved section. For example, if it's a nonlinear charge density, then all bets are off. Good? Sweet. Good. Well, let's go time permitting. I know this is already a little long, but why don't we do a second example here? Just for kicks. And I'll do this example not to find a new result. In fact, I'll keep the general situation the same. But what I'll do is, if I can find my pen, there we go. What I will do is let's go ahead and ask ourselves, rather than it being a very thin bar that is curved, what would happen if instead I had a quarter circle, but let's think of it as being a solid plate of charge? In other words, let's say that this has a radius of r and a total charge of q. How would our approach change? What do we need to do in order to solve that problem? Now, there will be a couple of changes. How we approach the overall problem. Now, we don't have a problem. Okay, there's no issue. But what we do need to worry about is charge densities. Okay. So first of all, rather than doing a linear charge density, what we define as charge per unit length, we're not going to do that in this problem. We are going to do an areal charge density, a charge per unit area. So that's one thing that we have to worry about. Let's go ahead and get the expression for the Coulomb force, thinking about charges per unit area rather than charges per unit distance. Well, first of all, let's go ahead and consider a uniform charge density. So again, you could think of uniform charge density means that the sigma stays constant. And so for one of these, we have a total charge Q. And rather than thinking about the length, pi over 2 times r, rather than thinking of that length, we now need the area of a quarter circle. You say the area is pi r squared. And since it is a quarter circle, it is 1/4 the area. And over on this side, now we have to think sigma is a charge. I'll put a small, tiny charge per unit area. Okay. So just like when I was doing the length of a wire, ds representing the infinitesimal arc length of the curve, here dA will represent an infinitesimal patch of area. And so what we find is that 4q divided by pi r squared dA is equal to dq. Okay. Now we have to understand, how do we calculate a small piece of area. Well, in Cartesian coordinates, you'd say, not a problem, I understand. If I have some area, notice I've drawn a square, okay? But if I have some area, a small patch of area, like, if I want some infinitesimal piece of that area, I can simply take the width and multiply by the height. I agree. Okay. So in Cartesian coordinates, we would simply say the area is dx times dy, a width times a height. Now, we could do, maybe I'll post an example problem of solving this specific case in Cartesian coordinates. Can be done, as we've seen. A lot more substitutions basically are involved. Here, though, since we have a rounded surface, there is probably a better way to approach this. Now, first of all, we can still use the idea that the arc length, ds, you can think of that as the height of your quote-unquote little patch. Okay? And so ds represents essentially, what we're trying to do is find the area of, say, a patch that's not square or doesn't have 90 degrees and straight sides. What we need to do is figure out the area when the patch has rounded sides, circular sides. But you already know this. Imagine I have this rounded patch. Let me go ahead and draw that in a different color. Okay. Draw that in as a different color, where this represents, I don't know, the distance from the origin. We'll call it r. And this little piece is an infinitesimal step away from the origin. In other words, this is an infinitesimal step away from the origin, what we usually refer to as dr. So the patch of this kind of curved segment, the area would be ds times dr. An infinitesimal change in the arc length times an infinitesimal step away from the origin. Well, now we should substitute in what is an expression for the arc length, ds. Good. And we recognize that this is an infinitesimally small angle. And so at the end of the day, we get that the area, dA, is given by the radius of whatever circle I'm considering, the distance from the origin. I shouldn't say radius. I should say the distance from the origin times this small angle. That combination gives you an infinitesimal arc length. And then I multiply by dr. These two expressions are 100% equivalent, but they are expressed in different coordinate systems, if you will. Okay? One being more particular for rectangles, straight edges, 90 degrees, maybe not even 90 degrees, straight edges. The other one is more appropriate for curved edges. And a lot of the time, I'll say, if that doesn't make sense, pause the video, go back, start thinking about it, mull it over. Okay. But this often comes into play is getting the problem set up, both in this class and beyond. Getting the problem set up, a lot of it hinges on which coordinate system do I want to use? How do I express a length element in that coordinate system? How do I express an area element in that coordinate system? How do I express a volume element in that coordinate system? And you'll see those pop up often enough that you'll start start now trying to understand it, but it'll keep coming back. And so hopefully the more you see it, the more sense it'll make, the more comfort you'll have with it. Well, at that point, we can substitute that expression in. I'll go back to red ink here. And we have something that says 4q times pi r squared. Now notice this is the outer radius of that charge distribution. Okay. This r, this lowercase r that I will now substitute in, lowercase r d theta dr, dq. This lowercase r is the distance from the origin to the patch that I'm actually considering for that small moment in time. And generally, again, that will be the case. I will usually use capital R for lack of a better term, I'll say a known distance or the maximum radius. And lowercase r, as you'll see, is an integration variable. Good. All right. Well, the second thing that we need to think about is what is the position of that little chunk of charge? And again, I apologize. We'll put the system again at the origin. You said, well, wait a minute, Greg, didn't we already find the position vector of that little chunk of charge? We've done that earlier. We said, okay, it's at location x, y, 0. Right? And then I converted it over into polar coordinates. That actually stays the same for this situation. Oh, excuse me, one minor byline. No longer are the chunks of charge located on the outer rim. They could also be inside. Right? So I should not use a capital R. I should use a lowercase r. My apologies, Greg's getting lazy. Well, the relative position vector between the system charge and this little chunk is calculated the same way that we have already done. Right? And so I end up with a negative r cosine of theta sine of theta, d theta. Oh, excuse me, not d theta is 0. And as you astutely have already noted, the magnitude of that vector is simply r. And so we are now again at a position where we have everything needed to calculate the small infinitesimal force due to that small infinitesimal charge. I guess I will practice what I preach and start by writing out the most general form of the expression. And now let's go ahead and substitute in all of our variables. We have K, system charge. Here's how far away the infinitesimal charge is from the system. And then we have this old rigmarole, 4q over pi capital R. Now this one is indeed a true capital R. Let me go back and double check that I haven't missed anything. Okay. And then we have lowercase r d theta dr. So there is my infinitesimal charge amount dq, just to remind us. And then we have r hat. Well, r hat is simply negative cosine of theta, negative sine of theta, comma 0. Yeah, and you probably already see it, right? You say, oh, okay, we got to do 2 integrations. Well, technically, we have to do 4, right? Notice now, because I am doing an area, I have to perform 2 integrations. One according to the distance from the origin, and the second one according to the angle. Good. So let's go ahead and consider the x component of the net force. So what I want is the x component of the net force. And so we see KE, we have the 4Q. Those are all constants. I will pull the constants out. And then we will have to add up. And notice I have a lowercase r squared in the denominator, a r in the numerator. So that will result in an expression of 1 over r. Cosine of theta, and we have a d theta dr. Oh, negative sign. There we are. Well, first of all, some calculus for you, right? Because I have two integrations to perform, this is sometimes referred to as a double integral. When our lowercase r does not depend on theta, or when our theta, our angle, does not depend on the value of lowercase r. In that particular circumstance, doing one double integral is like doing two single integrals. You can do them independent of one another. So the first thing, and I'll tell you they are independent. So the first thing I should ask you, what are the limits of integration for theta? Yeah, good. You see that for theta, we go from 0 to pi over 2. Now, another notation issue. Okay? When you're faced with a double integral, when you're faced with a triple integral, when you're faced with however many integrals the problem throws at you, okay? The general way to write it down, this is a notation issue, is that the inner integral sign goes with the first, for lack of a better term, I believe we call this a dummy variable. So it is understood implicitly that this integral, the inside one, goes with the first dummy variable. The outer one goes with the outer dummy variable, et cetera, et cetera. So if you had 3, think of it going outwards. Now, what are the limits of integration of r? Yeah, good. We started off at the origin, right? We have little charge elements located at the origin all the way out to a maximum of big R. Okay, good. Yeah. Okay, well, let's go ahead. Since r, lowercase r, is independent of theta, right? Lowercase r is a constant with respect to theta. In other words, it does not vary according to theta. So doing a theta integration, we don't have to worry. We can almost treat that lowercase r as a constant when doing the theta integration. So what that means is that I can write this. I will rewrite it in a manner that is a little bit, perhaps more intuitive. This is an equivalent way of writing it. And now again, notice that I do that integration and it will give me some number, and then I can do this integration. Well, you say, Greg, I already know what the integral of cosine is. Say, well, that is the sine of theta evaluated at 0 to pi over 2. But what's the sine of theta at pi over 2? Good, 1. Sine of 0? 0. And so we end up with, you notice that's a constant, right? This term right here is just another constant. And when we're doing an integration that has a constant, we can pull the constant out. Right? So we can rewrite this, and then the integral of 0 to capital R. Excuse me, nobody saw that. Good. Of course, the integration of 1 over R, that might be one that you might be struggling with that. You might think, oh, I can just do a power rule. But that's one of those that the power rule doesn't really work. This is the ln of r evaluated at 0 to r. Now, of course, you as the astute student know we should have defined at the upper limit, we should define at the lower limit. Okay. And this is where we're going to run into, Greg, you're silly, you have created a problem that is 100% non-physical. Right? You say, wait, what? How? What? Where? Where? You go, what is the ln of 0? Yeah, sorry guys. Undefined, right? This is undefined. And that should make some sense. Greg wasn't thinking, right? Right? Greg wasn't thinking. Why is this undefined? It's because at 0, when the source charge is located at 0, it's at the origin, which means the source charge and the system charge are exactly in the same spot. And if I want to calculate the Coulomb interaction between two charges that are located exactly at the same spot, I don't mean sort of close, I mean exact, the separation distance between these two charges is 0, and the Coulomb force is undefined, division by 0. So how do we get around that? Oh, that's a good question. Let's do it like this. Okay. So Greg set up a silly problem which ends up giving you an undefined. Let's go ahead and define a new variable. I'll call it R0. So think of this as being where we want to start that semicircular arc at. Okay. And then we can get an answer. We could say the net force of X is equal to negative 4 KEQ over pi r squared. And what we'll do is, let's say we have the ln of r minus the ln of wherever we want to start the circle at, R0. And we can make R0 as small as we want. You know, you can make the limit as R0 goes to 0, right? But you can't set it exactly equal to 0, otherwise we end up with undefined. I can take ln of r minus the ln of R0. I can write that as the ln of capital R divided by R0. There we go. So the x component of the net force is right here. And again, I apologize. We make R0 as small as we want, as long as we don't set it equal to 0. And boom, we have it. I've already made the comment, but I'll remind you. Say, what about the y direction? We will get the same result for the y direction because of the symmetry around the line angled at 45 degrees. So I won't do that one, but I encourage you, go ahead. If you don't believe me, go ahead and work through it. You'll find the same result. So, good. Well, I'll leave it there. Maybe I'll post a couple more example videos doing maybe volume elements. Maybe we'll do some surface elements. So maybe like the surface of a sphere rather than, a flat surface. But that'll be for, viewing pleasure, but also to help get you more familiar with some of these other coordinates, a little bit more of the integration techniques, et cetera, et cetera. So, well, I'll leave it there. Thank you for your time. Keep up the good work. I'll see you next time.